Everybody, come to the front. There's loads of space. We've got a really exciting session all about surface operations and the technology to enable exploration of the moon. So without further ado, we're going to jump right in. I've got my colleague from ispace coming up here to talk to you about the field testing of the ispace Tenacious lunar rover, which we did across multiple terrain analog sites. So Philippe Ludivig, welcome to the stage, and the floor is yours.
Okay, let's get started then. So first of all, I'll give a brief recap of the Tenacious rover. So this rover, we launched it early last year with a landing attempt in June of last year. The rover was built in less than 3 years, and it's a really small rover. It is 5 kilos in total, and it has a differential drive configuration with 4 wheels. It uses solar power. It has a communication via the lander, so we don't have direct-to-Earth communication, but we use the lander as a relay. And it's designed to only last a single lunar day, so we really focus on trying to operate as fast as possible. And there's 2 customer payloads on this. On the rear of the rover, we have the Abbie scoop, which is essentially a shovel that we use to collect regular simulant. And then on the front side, we have the moon house, which you can also see in the picture here, which is more of an artistic payload where an artist wanted us to bring a small house to the moon and to take pictures of it. Now, the mission that this flew on is the ispace mission M2, the resilience lander. And the primary goals for the surface operations of the rover were payload operation, mobility testing, and also collecting science data. So why is field testing important? Why don't we just stop at vibration testing and TVAC testing? But actually, once the rover is built, we still have a lot of things to figure out. So on one hand, we want to really validate our design. We want to check if in realistic operations our design actually makes sense. We want to check if the software makes sense. And actually, when we go from just flat set testing to multi-hour or multi-day field testing, we actually found a lot of issues that didn't show up right away in testing. So it's actually very important to do this kind of testing. Now then there's also procedure development. Of course, we do have procedures for all of our subsystems before we go to field testing, but once these procedures hit reality, we really adjust a lot of them. And this is especially true for our customer payloads, where we kind of have some sort of interaction between the mobility of the rover and how the designers or the customers of the payload actually intended to use the payload. So we actually sit down with the customers and really go through their subsystem and see how we use this for real. Then next up, there's the operator training. So this is probably the most obvious thing that we need to do. But in our case, because we have 16 operators, so we operated in 4 teams of 4, so 3 teams that work for 8 hours each, and then a backup team. That's a total of 16 people that you need to train. They all need to know all the subsystems, and also in our case, these operators are not full-time operators. They are the engineers that build the rover, and we need to account for them learning how to do this type of operation. And lastly, there's system characterization. So you'd think we know from the data sheets exactly how the subsystems work, but for some of them, we actually still need to measure what the output is. This is especially true for the wheel odometry, where the slip ratio of the wheels actually affects how far the rover drives for each driving command. And it's very important to measure this. Now, for the actual testing sites, we started with our indoor testing facilities. So we have our very own, or we had our very own ispace lunar yard, which was a 10 by 10 meter indoor facility using basalt sand with harsh lighting conditions, just as what we would expect on the moon. It was not perfect in the sense of there's no regular simulant, and you can always get more fidelity, but what was really useful was it was there every day. You could test every day, you could do your operator training every day, and we really made use of this. Next up, we were lucky enough to be able to use the facility of the University of Luxembourg, which also has a similar facility, but with the help of a very dense motion capture camera system. And this was more for the characterization of the mobility. So here you can see how this was used to check how the mobility performs in different inclinations. And then lastly, we use the brand new facility of the European Space Agency at EAC in Cologne. And this is a large-scale indoor facility with about 1,000 square meters of regolith simulant that ended up being really important for our testing. So here you have the mobility system that is stressed, but also the cameras that are stressed. And it really is good for all the items we wanted to test. But then going forward from the indoor facility, we actually want to test on a larger scale. Our rover can drive up to 1 kilometer away from the landing site, so the scale of these facilities really becomes the problem. So first of all, even for just simple characterization like the radio systems, just going to an open field sounds dumb, but still useful. Next up, we use the quarry as well. So this is not too far from here, just across the border in France. We were able to do regular testing as well. So this doesn't look like the moon, and the surface is also relatively hard. But on the other hand, we can drive 500 meters, 1,000 meters, and the operators can really learn what it means to do long-distance driving. And they can also practice localizing, so orienting themselves with the position of the sun. And then lastly, we did proper end-to-end testing in the Canary Islands, because there's some volcanic eruptions there, which means you have basaltic surface material over larger areas. And again, here it's very visually realistic. You can do long-distance driving, and you can even teach your operators to learn how to drive with satellite imagery. But in the end, not one of these facilities managed to get us to the goal, but the combination of all of these locations. So we can do regular end-to-end testing, we can do mobility characterization, we did operating in regolith simulants, we really tried to use realistic illumination, we did long-distance driving, and we were able to navigate with orbital imagery and the help of the sun. We also tried to simulate how communication works. So we actually had a simulated lander that was relaying the data back to our operations center, and we limited the bandwidth, and we also tried to test the time delay. And actually one of the things we found here is that the bandwidth limitation is way more important for lunar operations than the time delay. We also spend a lot of time testing which kind of imagery you would use in order to conserve bandwidth and trade how much situational awareness you need in comparison to data that's available. Now, the lessons learned here are really every site that we use is unique, has its own benefits. Bandwidth is really much more important than latency. You do need to do regular simulant testing to really account for how your mobility system works. You also need to train under harsh lighting conditions to figure out how to use your cameras. And especially your operators will usually not be experts in all the camera settings, so that's also something you need to teach. Orienting the rover via orbital maps of the position of the sun is equally something that you need to teach first. And lastly, training can be boring and operators can be lazy, so you really need to figure out strategies on how to keep your operators engage throughout the whole training procedures. Because we're talking about days of testing, not just a couple of hours. In conclusion, I can say that we validated our onboard rover software, so we were very happy with that. We tested across 6 different sites. We really refined our mission procedures from what we initially had. We trained a total of 16 operators over the course of 35 days of operations. And even though the landing was not successfully ultimately, we take these lessons really into our future rovers. So for the next 2 rovers that we're building right now, we already have some lessons learned that flow into the design, as well as the software that we use to drive the rover. And field testing will remain a core part of our operations strategy. Thank you.
Fantastic. Okay, we've got 2 minutes for questions. Any questions from the audience? Hands up. AJ?
Hi, how did you simulate anomalies or off-nominal operations during emission training?
So during some of the early testing, we did fault injection. So sometimes you can have software modes that are not as you would want them. But honestly, in the scale of the testing, and you'd think that this is a small system, we had a lot more issues than we initially expected. So in the future, we would want to do more anomaly testing, but yeah, there was only so much time to do everything.
Thank you.
Thank you. Any other questions? Yep, we have a couple over here.
Hello, great presentation, first of all. Thank you so much. You mentioned at the end that it's very important to test against challenging illumination conditions, I guess. Is it something that you mainly do in lab or in an analog facility or like in field tests? And if the second case is the one occurring, how can you control this? How can you make sure that you can validate? How can you get sure that it's kind of similar to what you will observe on the moon? Thank you.
Okay, so most of our illumination testing happens in indoor facility, especially the lunar facility in Germany is very good for this. It is smaller in scale, but you will see the same type of illumination. So you have a very strong sunlight there. We actually measured how strong it was in different locations. And you also have the same reflective properties of the surface material. In an outdoor facility, you could technically do this at the night, doing a nighttime test when you bring your own lights. But the scale of trying to organize that meant that we decided to deliberately to only test illumination in indoor facilities.
One final question, yep.
You mentioned about all the operators. Do you plan on having some autonomy in the future on the next rovers?
Yes, very good question, and we definitely want more autonomy. The reason we had limited autonomy on the first rover was time to development and limited processing power. But in the future, we want to develop more and more tools that support the operators, at least to have some semi-autonomous systems that still need supervision.
Thank you very much. Okay. Thanks, Philip. Right, next to the stage, we have co-founder and CTO of Lunar Outpost, AJ Gemmer. He's going to be talking to us about the Lunar Outpost Eagle LTV. AJ.
All right, thank you, Abbie. It's a pleasure to be here. As Abbie said, my name is AJ Gemmer. I'm the co-founder and chief technology officer of Lunar Outpost, here to tell you today about the mobility systems that we're developing to enable space resources exploration and extraction and the establishment of critical lunar surface infrastructure. So our founding philosophy is that Lunar Outpost is developing the technologies to enable a sustainable human presence in space, building up to NASA's Artemis moon base vision. Since launching our first mission in February of 2025 last year, we've become one of very few companies that can say that we have operated on 3 separate planetary bodies. So that's our MAP rover that operated on the moon at the South Pole, Mons Mouton, last year. The MOXIE experiment aboard the Mars Perseverance rover, making oxygen from the atmosphere on Mars, one of the first ISRU demonstrations on Mars. And of course, we always work to have a technology flow back here to Earth and expand our technologies into resource extraction operations here as well. To do this, we establish a cadence, a regular cadence of our flight missions. So right now, we're at about 1 mission per year and aiming to increase that cadence as we go. Like I mentioned, the first rover launched last year in 2025. Our next rover launches at the end of this year aboard the IM-3 lander to a near equatorial site, Reiner Gamma. Our third mission is a commercially supported mission, again going to the lunar South Pole. The fourth mission is Australia's first moon rover, Rover, shown there on the slide. And as we look towards the future, we are adding additional capabilities and critical technologies, things like human-robot interaction with the Artemis Deployed Instruments program, shown on the far right, as well as astronaut mobility through the NASA Lunar Terrain Vehicle program. And so this, in addition to those ends of the spectra for our mobility systems, we also have multi-scale robotics in between as well, such as the 500-kilogram Eagle rover platform shown here. This rover is especially adapted for resource extraction and exploitation, things like moving 12 tons of lunar regolith simulant in 12 days autonomously during the NASA Break the Ice Challenge. And that brings us to the Lunar Outpost Eagle LTV. This is a rover vehicle that was really designed to be a work truck for our Artemis astronauts on the moon. It's tough, it's rugged, it puts their tools right where they need to be, provides cryogenically cooled sample storage for them to return their volatile samples back to their ascent vehicle. And for most of the vehicle's 10-plus year lifespan, when crew are not there, it can operate autonomously and perform infrastructure, cargo, and logistics operations at wide range of latitudes on the lunar surface. So some examples shown here of how the Eagle LTV is equipped for those types of autonomous operations, things like digital elevation and terrain mapping, multispectral spectroscopy of the lunar surface, gathering samples using a robotic arm and sample container, as well as the large infrastructure and logistics operations, things like towing trailers, establishing power and communications. And in order to serve as this work truck for the moon, as the backbone of lunar surface infrastructure, the Eagle LTV is designed to be interoperable with all other proposed surface elements. And this takes a variety of forms. Interoperability can mean power exchange between the Eagle LTV, habitats, or other mobility systems, as shown here. And that allows both our systems and those other systems to survive the night longer and explore deeper into permanently shadowed regions. The Eagle is also designed to be interoperable in communications, so serving as a relay between other surface assets and our crew and its onboard facility instruments. I've already mentioned logistics, the Eagle's ability to deliver, deploy, and service other surface elements and moon base or habitat architectures. And it leverages its very high cargo capacity to move those large payloads around the surface and interchange between resupplied instruments and payload deliveries. And of course, our focus on resources, so the ability to map the surface, to perform subsurface sampling and excavation, and bring those samples and materials back to the Artemis landing sites and the moon base sites for further analysis. So this is a vehicle that is very mature. In fact, all of our mobility systems are at least TRL6 and share a lot of components and key subsystems and software across all of the platforms. So we have built 5 drivable prototypes of the Lunar Outpost Eagle LTV, shown here, which we test thoroughly at our facilities in southern Colorado. We have a 1,000-acre autonomous test facility down there. So I'll end with a short video that highlights the spaceflight heritage of some of our teammates on the Eagle LTV, General Motors and Goodyear, both of whom worked on the Apollo LRV and are now contributing their latest technologies to the Lunar Outpost LTV.
NASA scientists and engineers anticipated the need for a vehicle to aid the astronauts in exploring the moon. It was expected that bulky spacesuits and other inherent weaknesses would decrease man's mobility on the lunar surface.
So as you can see, we're very excited to be supporting NASA's new Artemis vision and the future of space resources, which is already well underway. So I'm happy to take any questions at this time.
Thanks, AJ. So, any questions? Here at the front.
Thank you. Clive Neal, University of Notre Dame. AJ, fantastic stuff. Lunar Outpost has really grown quite a bit. Question about your MAP rover. Can it be retrofitted for an RTG power supply?
It's a good question. So I'm a big fan of radioisotope heating units and RTGs. Of course, that would be a game-changing technology to enable really long-term, multi-year missions on the surface. So the short answer is yes, we have done some integration activities investigating the feasibility of including either an RTG or an RHU aboard all of the different systems. So that's something we really would love to work with a specialist in radioisotopes to develop.
Please, expected range for night operation on batteries.
Yes, so for the MAP rovers, the overall range for a single lunar day is about 2 kilometers, and then we would attempt to hibernate through the lunar night. For those larger systems, Owl and Eagle, those vehicles do have sufficient battery capacity to do limited operations during the lunar night, primarily positioning, sampling, things of that nature. The long duration drives, especially with crew, of course, would be performed during the lunar day.
Another question over at the side.
Thank you. So my question is, is it going to have the rubber tires on the moon as well, or is that just for Earth demonstrations?
Good question. Those are our Earth testing tires. So Goodyear has created tires that look similar to the Apollo LRV, the spring wire mesh tires, but packed with modern material science and technology. So those are the tires that the Eagle LTV will use on the moon.
Thank you.
I think we're nearly out of time for questions right here, but feel free to grab AJ later.
Thank you.
Okay, next up we have a speaker from Space Applications Services, Hemanth Madakashira. Hi, I hope I didn't butcher your name completely. Hemanth Madakashira. He's going to be talking to us about the passive suspension system breadboarding and reduced gravity mobility testing of the LPSR. Hemanth.
Thank you very much. Good afternoon. Hemanth Madakashira, team leads future project and exploration team at Space Application Services. We are working on LPSR. We're not just one. We are one of the 3 consortiums. Parallel studies are going on, and we are one of the 3 consortiums working on LPSR. And before maybe going to lunar prospecting and scouting rover, LPSR, before going on the bedboarding aspects, maybe I would just summarize what the rover is about. And the key objectives are to deploy the first European mid-sized rover in the sense of 350 to 500 kilogram rover, and to advance and mature any technologies that are required for large 1-ton rovers that are majorly used for transportations, logistics, or even it could be for human missions as well. So, and also to learn or master the operations in a challenging environment, especially in the lunar South Pole regions, and also shape the next generation for the future rover aspects. So to achieve the mission objectives, the key functionalities that are required are to be able to navigate faster, navigate autonomously, to move in all terrain, ranging from 20-degree slopes, even higher slopes, and built to survive in extreme environment in lunar South Pole regions where the lunar nights could be devastating, with the thermocyclings going from 90 Kelvin to 410 Kelvin, and radiation, dust, and all the extreme temperatures need to be protecting from against it. And also to be able to use the existing resources or future resources that will be deployed on the lunar orbits, communication relay satellites, or even any precise navigation from LCNS, the satellites. So just to give you an overview, the entire system of interest consists of a space segment mainly. The rover platform, which is about 350 kilograms to 500 kilograms. The variation is mainly because of the night survivability, either to survive short nights or long nights, depends on the CONOPS as well. We majorly focus on the payloads that really support navigation aspects, which is for the mapping payloads or technology demonstration payloads for night survival, dust mitigation. And science is an opportunity. And in prospecting and sampling payloads, there are a lot of opportunities for such scientific payloads. Offloading is part of the space system to offload the rover from the lander to the lunar surface. Surface communication is optional. It is mainly our rover is usually able to traverse to about 100 kilometers. So surface communication is really optional. It only provides communication few hundreds of meters. So we chose 2 landing sites. One of them is the Shackleton-Girard connecting ridge. This is a very good site for scientific purpose, although it has a very high illumination sites, but not a good Earth coverage. The second one is one of the Argonaut landing sites, which is Malapat Massive, and this site has 100% Earth coverage, and also has a good amount of sunlight, average sunlight, more than 80%, I would say. So what we chose some constraints for the path planning of the rover. One is to go in the low risk path in the beginning, which is to aim less than 20-degree slopes, or to avoid anything which is beyond 30 degrees, and maybe to traverse to some scientific interesting areas if it is within 20-30 degrees. And we put all of these kind of criteria into our model, and then we came up with some kind of path plans for both the missions. You can see it's the Shackleton-Girard Ridge landing site here, and the other one is Malapat Massive. And we have a first initial 3.5 kilometers, or maybe about more than that, is a safe region where we traverse only to less than 15 degrees or 10 degree slopes, and we cover majority of the science there. And we do the extension of the mission towards highly illuminated regions where we could extend the mission even for 6 months. Same goes also for the second landing site, which is massive, where we can extend the mission even, we can cover all the scientific aspects there and also extend the mission to several days. I can talk about, we have developed some in-house tool for this. Maybe I can talk about it later. This could be not only used for the mission analysis, but further it can also be used for the ground segment and operations as well. So we have a chance of performing some breadboarding. So there are a lot of aspects to do breadboarding, right from night survival, dust mitigation, autonomous navigation, anything to do with the all-terrain capabilities. So we chose a couple of breadboard options. One of them is vision-based navigation and autonomous navigation, which is here, which is performed by our partner, Michelin. They are located in France. And we at Space Applications, we did some passive suspension system, which is very much similar to the LRV. So it has a similar kind of concept. And so at Michelin, they have first validated they took the rover model and then tried to validate that in the software to see how the software performs. And then at the same time, in Space Applications Services, we build a kind of a rover and also the passive suspension system. And then we tested it in a space application facility that you can see in the image. We also have a partial gravity offloading system, so we test the rover with 1G, 160, 38G, and whatever it is. And we took a lot of points, the rover moving on the boulder, on the slopes, on the side slopes and everything, and we recorded those data. And I think the video is not playing on the last one, but we had integrated testing performed with the GNC at Space Application Services, and where we have mitigated, or we have tested it in the lab, how to climb the obstacles, how to go through the obstacles, how to avoid obstacles, and all of those. And so once we have that, we have confidence to test in the Luna facility. And this image you can see now is that we tested the integrated platform, both passive local suspension system and as well as the GNC breadboard in integrated system in the Luna facility. And there is a video. Oh yeah, thanks for playing video. But I will go to the next slide. Maybe I have to press the next one, yes. So we did, you can see the landscape photo of it. This is the Luna facility. And we tested it majorly in this location. In the dark, when it is lit, we don't see any artifacts or the features, but then the camera can see what it can, and we did test in several. One of the key things that we want to test is dark shadows on the Luna South Pole. That could be very devastating for autonomous navigation. So we would like to gauge how the autonomous navigation system, vision-based, can deal such a long shadows. So we did test with rover going towards the sun. There is a sun illumination aspect or simulation there, and with the light beam. And we went towards the sun, and we went away from the sun, so that there are deep shadows casting ahead of us. And then we tested with the artificial lights and without artificial lights. We took down several information, several data of what are the performance of the GNC, and as well as the performance of the passive suspension system that is already integrated on it. We are currently now analyzing these data, and most likely to publish within 2-3 weeks these data. And a special thanks to Aiden and all the team who helped us make this happen in Luna facility. And yeah, that's it. And I think this video keeps on going, but if you have any questions, yeah, please.
Thank you very much. Questions? Don't be shy.
Hello. How are you planning to perform vision-based global localization for long-range drive on the moon, on the lunar South Pole? How can you actually localize?
Oh, yeah. So that's a good question. So what we did is we took a photo of Luna for the localization, and then we degraded the photo to 5 or 10 meter per pixel, because that's what we have currently. There was a very good, nice debate before this session on the same information data. So currently we don't have that. So we imposed that, and we made a high-level path plan. We identified the artifacts that we could see with 5 or 10 meter per pixel, and we used those artifacts as a location triggerer. But in future, we could also use something like star tracker. That could be also one of the options, but this is, I don't know how to use that exactly. Sun sensor and star tracker can also be used, but they are not representative in such testing facilities. So we use artifacts.
Any other questions? Maybe one from me. Your passive suspension system, is it individually by wheel, or are the wheels combined in any pairs or linkages?
No, the passive suspension system is completely different. It's it connects the wheel to the body, I would say, and it's based on the torsion rod. So it's same as LRV, I would say, but then it has a little bit different mechanisms. We have 2 torsion rods to support, and each one has when there is a required twist, it will try to compensate it. Yeah.
Thank you very much. Okay, I think we're nearly out of time. We've got one quick question, hopefully a quick one with a quick answer.
Hey, thank you. I just wanted to ask, how do you plan to deploy the rover from landers?
Deploy from, we have several concepts, which is not part of the study, but no, it is also part of the study. And a couple of options are there to have, if the rover permits a steep deployment, then yes, why not use steep ramps and something else to support the rover? If not, there are a lot of other studies ongoing. Like the crane-like system, so that it has a simple 2 degrees of freedom to lift and drop the rover from a height of 4 to 5 meters maybe. But if the height is too short, then I think a small ramp-based system should be good.
Okay, thank you very much. A very interesting update on LPSR. Really glad to see it. Okay, up next we have a colleague, also from Space Application Services. Welcome to the stage, Simon Vanden. He's going to be talking to us about the Love Me M lunar rover.
Yeah.
Welcome, Simon.
Thank you very much. So good afternoon, everyone. I'm Simon Vanden. I'm a project manager at Space Application Services. And I will talk to you about one of our other rover projects that we have running, which is called Love Me M. It's actually part of the Love Me rover family, which is it has a history of more than 10 years and being developed under ESA and European Commission funded projects. And Love Me M is just the latest member of that family. But let's say it's the first one that we are really designing to cross the technology gap and to make a flight design out of it. For the Love Me sizing, we have decided that the sizing you can see here is basically the sweet spot we have at the moment in terms of availability of different landers, availability of different payloads to go on the rover. So we're talking about a 40-kilogram lunar rover with our big target to achieve a 1-to-1 mass ratio between platform and payloads, which is driving a lot, of course, the design of the rover. Wheel diameter 20 centimeters, and the dimensions are 60 by 60 by 50 centimeters. Recently, we were talking to some journalists, and they basically described it as a built-in oven in your kitchen. That's what you can imagine about it. The rover is designed to go to landing sites with polar and mid-latitude locations, which means it does have solar panels in the vertical direction. There is also an option for a deployable panel on one side, radiators on the top. And we have decided to go for a redundant communication link, a link through the lander as a relay and one with an orbiting relay. As I mentioned before, 1-to-1 ratio between payload and platform means we have taken a lot of care to give all the potential payloads a lot of options of where to go on the rover, on how to interface with the rover. As you can see here, we have a lot of potential payload bays, which can have views towards the regolith, can have views towards the top, towards the front, different directions for different kind of payloads that can go on the rover. You can find more details about all of this in the user guide, which is available on moon.spaceapplications.com. Also about the electrical interfaces, we have 3 different potential power buses for payloads. We do have quite some power available during driving and also during standstill operations. We have reasonable data volumes as well. So we're happy to talk about any specific requirements you might have. Similar to what was done for LPSR, we have done a mobility and navigation breadboarding campaign already in the past year. I'm not sure if this is gonna start the video. Yes. This is the video that was taken at the Luna facility, so thanks again to the ESA and DLR crew for hosting us there last month. Here you can see a bit how the rover drives, and this is really what we've been able to validate at this facility. For this small rover, we're aiming at speeds of up to 5 centimeters per second and slopes of 15 degrees. Besides the test at the Luna facility, we also do have our own in-house, what we call the moon yard, similar to what Philippe mentioned for ispace. This really allows us to do the day-to-day testing. It helps us a lot. We were extremely well prepared to go to the Luna test because of this facility. And the very nice thing we have in here is that we both have a motion tracking system here, so it allows us to have some really nice data, as well as a gravity offloading system, which you can see in the picture on the right. And this is a system that we have developed in-house, and that's also installed at the Luna facility, actually. So, as I said before, we have done a large range of tests with this locomotion performance model. We have successfully already validated a lot of the thermomechanics of the rover, a lot of things about how the rover handles, how well we can control it, how it handles obstacles and craters, and all of those things. And the other thing we've done during this test is a first test of teleoperated navigation. So as you also heard in the ispace presentation, it's really not easy to get sufficient situational awareness on a rover like this with only a limited amount of sensors. And so this is also something we wanted to test already now in this phase of the rover development. What can you imagine with this, with navigation of the rover? We have a limited set of onboard autonomy, really focused on keeping the rover safe. And then we have a lot of the driving itself is done by supervised autonomy or with teleoperations from our ground control center. We have a lot of sensors on board of the rover. We have a couple of cameras. We have other sensors as well for wheel odometry, and we also do have a star tracker to help with localization. And as I mentioned before, a redundant communication link, which of course provides us redundancy, but also allows us to drive beyond immediate lander line of sight. The rover is designed for a variety of missions in polar and mid-latitude, but for mission 1, we are really focused on lunar South Pole landing sites and for single lunar day operations. During that single lunar day, we want to drive a distance between 3 and 5 kilometers with a lot of potential stops for measurements or science. And we do foresee in the design a possibility for excursions into shadowed regions for up to 2 to 3 hours. Mission control, I briefly mentioned it before. This is something where the company has a lot of experience, a lot of background. We have been running a control center in Belgium already for more than 20 years. So that's also the one that we're going to use and expand for the rover operations. And the ground segment will be based on our own YAMS software, which is also widely used in the space industry for satellites and also lunar projects. Timeline for mission 1. So as I mentioned, mission 1, there we want to go to the lunar South Pole. Launch is planned at the end of 2028. So that's the timeline we have. For mission 1, we are mostly incorporating payloads which are already at a relatively high TRL, so that they can have a flight model delivered to us by the end of 2027. Of course, we do foresee future missions after mission 1. So even if you would have a potential payload or experiment that does not have that kind of timeline in mind, please do feel free to contact us. We'll be more than happy to work with you for future missions. Next steps, what are we doing at the moment? We're preparing for 2 very important milestones right now. We have the rover PDR coming up in July, and at the same time we are now starting up the assembly for the rover EDU. Rover EDU is basically a structural and thermal model. It will go through mechanical and TVAC tests by the end of this year. And it will also have a part of functional avionics that we want to test on this model as well. So that's all. That's the summary of the LoveMeM rover. We've designed a pretty versatile rover platform. It's meant to really serve not for one mission or for one set of payloads. It's really meant to go on multiple potential landers, multiple landing sites. It can certainly be part of bigger prospecting campaigns and things like that. We'd be more than happy to discuss about these things. As I said before, first mission we have planned for end of 2028, beginning 29. And we do have a little bit of capacity left on this first mission. So if you have an instrument, a payload, which maybe is already at an engineering model level or at a reasonable TRL, feel free to get in touch with us at moon@spaceapplications.com, or also for any other thing for future payloads that do need a ride to the moon. We'd be more than happy to discuss with you. So that's all. Thank you, and I'm happy to take any questions.
Thank you, Simon. Really exciting to see. Okay, any questions for Simon? Philippe?
Thank you. Very nice presentation. I was wondering, you have a stereo camera. Have you considered mounting it on a mast? And if not, what was the trade-off of not doing that?
Yeah, we don't have a mast. So indeed, it's a trade-off. Let's say we wanted to avoid the complexity of the mast due to the deployable, and we do think that from the simulations and the analysis that we've done, that it will work out at the top of the rover height, let's say. Also from the test that we've done in Luna, we have placed it in similar position, and we do have reasonable, let's say, driving range, so enough so that the operator can make an informed decision on the next waypoints, let's say. So yeah, it's very much a trade-off, but I think for our rover design, this seems to be the best choice.
Thank you.
Thank you. Next question. Anybody? Yes, one in the middle.
You mentioned that spatial awareness is a problem. Do you have any other cameras around the rover, like hazard cameras, or any way of perceiving the surroundings besides the navigation cameras?
Yeah, we do have hazard cameras, indeed, on the rover. Yeah, as I mentioned before, this is really to provide a more, let's say, an onboard safety feature for the rover. So we have to see how much of those pictures we can actually downlink to Earth because of the bandwidth restrictions that Philippe already mentioned. But for those are exactly the areas where we see a relatively lightweight development, but adding a lot of value for onboard safety, let's say.
Thank you, Simon. I think we're out of time, but again, I'm sure we'll be able to find Simon outside and ask him more questions later. Thank you. Okay, next up, we have a slight change from the program. So we're going to be joined by Alice Dottori, who is from Politecnico di Milano, and she's going to be talking to us about small landers and how they can contribute to surface planetary exploration. Alice.
So good afternoon, everybody. I'm here on behalf of Professor Lavagna and of the Astrolab Research Group at Politecnico di Milano to present you our work in designing a small surface element to support large scientific mission with in situ measurements. So the idea is to design and build some small in the CubeSat class surface element and landers that are able to perform in situ measurement with also the collection of soil sample if the application is a non-cohesive soil environment, and have this surface element as simple as possible in terms of interfaces to be able to find accommodation in whatever big spacecraft. Okay, so as I mentioned, the idea is to stay in the CubeSat class for these elements. We can have the possibility to have a soil collection, and maybe you've heard something about on Tuesday morning presentation by my colleague, and also to have a reorientation capability of the surface element, because on the other hand, we want to have a propulsion subsystem. So once the mothercraft delivers us close to the surface, we will have an uncontrolled landing. So we are not able to control our attitude during the landing. But having this tilting mechanism, reorientation capability, will allow us to get to the correct orientation before starting the scientific operation. So yeah, the idea is, as I mentioned, is to be in the CubeSat class, specifically with a 4U configuration, so 20 times 20 centimeter with 10 centimeter in height. And with this configuration, we are able to squeeze the most and reduce the most the mass budget, while having like around 1 U of volume available for different payloads. Obviously, this depends if we need to collect the soil or not. We do not have, we do rely on the mothercraft for communication with Earth, or with the mothercraft or other relay spacecraft around the body of interest. And we need, because we select the 4U configuration, we do need customized mechanical interfaces with the mothercraft. We are considering typically having a separation ring with the mothercraft with an umbilical connection for power and data transfer during the transfer. So as I showed you before, this is some idea of the possible configuration with a 4U shape form. We can have flexible appendages, so we can have solar panels or deployable instruments or antennas if needed. And we aim to size our onboard batteries to guarantee at least 30 hours of operation with batteries. But then we also put some solar cell on the outside, on the lateral sides of the element to try to at least have some solar power. And in the red, in the picture at the bottom, you can see the tilting mechanism, so the mechanisms that enable us to have the relocation capability, and some example of payloads such as camera, dust sensors, and the sampling. This is an overview of the expected operations, so starting from the release from our mothercraft close to the surface, because we then have the uncontrolled and ballistic landing, followed by the bouncing phase. Once the bouncing phase is completed, we can check the orientation on the surface and perform tilting maneuvers if needed until we reach the final operation. And the idea is to guarantee at least 2 tilting maneuvers with batteries. Once we achieve the correct orientation, we can deploy our appendages, if any, and then start the scientific operation with the payloads on board. These are some graphs for the first part, so the descent, the ballistic descent, and the bouncing phase, which we simulate with a DM model that we developed in Politecnico. So we can simulate the interaction between the external shape of the lander and the non-cohesive soil, and study the possible bouncing evolution depending on the initial attitude. Okay, this is just a simulation in low gravity. Then, as I mentioned, we developed the tilting mechanism that is largely inspired by the Mascot relocation mechanism. So we have an eccentric mass on a flywheel. So we design it, and we also try to simulate this with the DM model I presented you before. So we can represent a lunar environment and a small body environment with very low gravity, and reconstruct the motor performances and the tilting maneuver evolution. And after having performed some of the simulation, we also moved to a breadboarding phase. So this is what is shown here is the 1G case, and we are planning to perform to develop a breadboard in reduced gravity to have more representative data. Then, as I mentioned at the beginning, we can also have the capability to collect soil in the order of grams or even below. And also, to support this design, we use the DM model that includes also the electrostatic force model in the lunar case, but also in the small body environment. So we simulate different configuration of the collector, and also here we start the breadboarding phase. So we define some possible configuration that could work in a reduced gravity environment while satisfying the constraint, mostly the 10 centimeter in height constraint. And we perform some tests, find out some nice conclusion, and send it. So the idea is to go back to the simulation to improve verifying the design and the operation. So yeah, this is was just an overview on the design we came up with for a 4U, but also 3U planetary small lander to support larger scientific mission on the moon, but mostly on small bodies. In doing that, we developed some interesting tool, mainly the discrete element model simulation environment that allow us to refine the design of the tilting and the sampling mechanism. And to develop that the more, we are, as I mentioned, we are working on the breadboarding phase and to support and also validate the numerical model. So yeah, that's all. If you have any question, I'm here. Thank you.
Thank you, Alice. That's really interesting to see. Any questions? Over here. Ben.
Ben Bussche, Intuitive Machines. Great talk, thank you. Quick question, what is the maximum altitude you're designing to be dropped off at that you will survive?
Sorry, the maximum
Altitude, height above the surface.
We are in the order of 100 meters, if I remember correctly. Then depends on the structure and the element.
Any other questions? You're going to have to put your hand right up, make yourself very obvious. Maybe a question from me. Is there any kind of calculation that you've done on what the largest planetary body is that you think that you could land on for the kind of coefficient of gravity that is survivable for this kind of a system?
Mainly we work with very small bodies, so like Martian moons and asteroids, so very low gravity, 10 to the -3. But then again, it's more a structural point of view problem.
Yeah.
So, yeah.
Fantastic. Fascinating idea. Any more questions for Alice before we let her go? Okay. You probably have some questions outside later.
Thank you.
Thank you very much. Okay, next up to the stage, we have Mark Fittock from OHB Systems. He's going to be talking to us about OASIS, a mission enabler for lunar surface systems. Mark, welcome.
All right, yeah. I'm very happy to be here today. We're a little newer project than a lot of the other ones that have been shown this afternoon, but it's my pleasure to, so to say, show OASIS to the world. We really kicked off in Q3 of last year. We're an ESA study at the moment, but going a little beyond that. Not a traditional study in the sense of what we used to do 10 or 15 years ago, but really approaching things from a different perspective now. And I have the pleasure of being the project manager here on OASIS, and it has been an exciting ride so far. And hopefully it will continue to be in the future. Oh, good, okay. There we go. So I'm in here showing actually a very early image from the Argonaut missions, but talking here about the problem more in general. So not just the problem of what OASIS is dealing with, but, okay, rather specifically, we're looking at lunar night survival, right? It's one of those challenges which a lot of early missions tend to look away from or focus on other aspects first. At OHB, we've done a lot of in-depth analyses and investigations about how best to go through long lunar nights, so not just looking at short survival. And in the end, we've got the thermal environment, the regolith, and one which often gets overlooked, which is the communication for payloads. And at the end of the day, the big one that OASIS is really meant to be there to deal with is the development and cost that payloads need in order to operate and to survive through those long lunar nights. And so we have what looks like this at the moment. And this is one of the reasons why I like to move around, also because it's late on a Wednesday and we've all had 3 long days at the moment. So OASIS is more or less just the blue box and the grey box with a nice big solar panel on top there. The idea here is taking some of that load off the payloads. So, yeah, we are effectively a platform system on top of a lander for the first mission. It's pooling key capabilities for these payloads, which means that, as you see in this picture, right, we have, as an example, 3 deployed payloads on the surface, a single payload on the lander deck itself, but then providing this effectively something like a service for future ESA exploration science missions as the study stands today. And one of the really big reasons behind all of this is just letting payloads focus on what they need to do to get their core mission objectives done, right? This is a classic challenge. I've been through that myself earlier as an instrument engineer. It can be very hard to deal with some of these, well, rather more standard systems when it's your first time trying to do those. So this shows a little more detail. As I said, we're a little bit earlier on, so I've got a lot of CAD pictures here. We're also quite early in that development. We are pushing at the moment towards a systems requirements review, so a lot of things are in flux. But I wanted to give a bit of a snapshot of where we've gotten to at this point today. You see the battery box up there, so that's one of the two. That's the big heavy one, as we refer to it. It's one of the big drivers for the mass. But on the other hand, it's what allows Oasis and the payloads to survive the lunar night at the end of the day. Down here at the bottom, you see the units box, which is otherwise referred to as the everything else box. So it has all of the units, everything which controls and enables control of the payload's communication, and the solar panels. This does not rely on any of the lander systems. So in Europe these days, right, we tend to talk about and think about Argonaut as the lander. And this does not require those systems in order to function, especially not for the first lunar day, not for the pushing forward into the lunar night. Also important, talking about enabling those payloads, is this deployable 6-meter power and data harnesses, something which is also sometimes overlooked, is a complicated enough challenge unto itself. And otherwise, yeah, quite important here, right? It is meant to be a payload agnostic system, so it's not designed for a single payload, but we are pushing forward with a payload as a first case, but that the entire system is still designed to be able to enable a different range of payloads. So maybe one larger payload, which is taking all of the power, or maybe 5 different separate payloads spread like I had in that picture before. And Oasis is nominally a lander-mounted unit. It is designed with that flexibility in mind that we can also go for direct surface placement, or even to be mounted to mobile elements in the future. I won't read all of these data points on this slide. This is really just here so that if somebody wants to come back and look or wants to take a photo, I can get out of the way for a second in terms of where we're at the moment. Now, there is 2 important points, and they're all right down here in the bottom corner. We are, at this point, around 175 kilos at this stage in the development cycle, right, with some margins, etc. But I think that's more or less where things are going to land, if not slightly heavier. And we really are in these relatively, for us, relatively small boxes. It is much smaller than the spacecraft we normally deal with. And in that sense, it is something like a simplified spacecraft from our perspective. I'll come to the reasons why it is not a simplified spacecraft in a moment. But it is smaller, but it is relatively heavy for what it needs to do, and that is all driven by the power storage. So the batteries are pushing up that mass. We need those batteries in order to provide the power to the payloads to get through a lunar night. That drives up the solar panel sizing, and that pushes most of it on the communication side. There we've got a lot of experience in terms of developing these systems, and right, effectively at this point we're iterating on those. And that still, oh yes, sorry, maybe the important point there is improving things like the data rate for payloads over having dedicated systems for them themselves. Yeah, I keep using this picture because I like it so much. It's relatively new for us to have these, of course, having only started late last year. The most important point here, because I sort of mentioned this, we're in a study phase, but we're actually working towards a PDR before the mid of next year already. So for us, quite a short-term, rapid development project. But we do have a series of breadboards. Like I said, it's not a simplified spacecraft, right? That is generally the perspective we look at from let's say an OHB system in Bremen perspective. So we are really trying to tackle the make or breaks in this case, right? We have a relatively short schedule. I'll show it in a second. I have to, I'm a project manager, right? I have to have a slide with a schedule somewhere in the deck. But here on the make or breaks, we have the thermal breadboard. That's clear. This system has to survive the lunar night if it's going to keep payloads alive in the lunar night. We have the harness breadboard. I mentioned that. A 6-meter long deployable harness on the moon actually turns out to be relatively more complex than it sounds. But we've got a really good team working on that one who have experience with the Martian deployed harnesses from InSight. On the battery screening, it's a bit of a funny one to mention as a breadboarding or a make or break item. But as I said, effectively, if we don't have that power to keep the Oasis system and the payload systems alive, that means we have a break. We haven't survived beyond or enabled. And the other, of course, at the end of the day, is the solar array mechanism. So bringing in enough power during the lunar day to get through that lunar night. And I mentioned the payload. I won't speak about it now, mostly for time. It's also the development of somebody else, I guess. But you can find information about what they're doing on Astrolabe online at the moment. It's a very exciting space weather and lunar environment monitoring station. So I said I had a schedule. I'll jump over it, but I'll only say one thing. We're driven to a delivery at the end of 2030 with a good 6 months of margin. This is in part due to the constraints on the, let's say, of the activity and the way it should be carried forward. We know that we could do this in 12 to 18 months less under different conditions, but we're very happy to be doing it and to be having a bit more time than we think we would need for a system like this for a change. Don't often get to say that for a project. I will jump a little here over the future for Oasis. I mean, this is more or less a list of the foreseen potential usages. As I said, it's at its core an exploration science payload enabler, but I'm here at Space Resources Week because we don't just see Oasis as being used for that in the future, but also other mission types. You see a lot of those here. ISRO is one of those ones on our target, of course. It lies within the strategy and the direction for us and building towards bigger and better things. And talking about bigger and better things, we don't plan to stop with Oasis at OHB. So this is the ESA study, what I present today. We have in parallel started an activity on our side as well, looking at not just what happens with Oasis, but also the work we've done on the past studies around the Argonaut missions and where we see the future for these lunar surface missions. This is a really important stepping stone for us in terms of building these capabilities, building larger, more complex, more advanced systems, but also providing potentially more simple systems. And at the end of the day, we want to look potentially towards commercial solutions, which means a different approach than what we do for ESA as a customer. Okay, maybe I should mention the name because I've jumped through all of what we're doing on it, but yeah, it's picked up the nickname Lucy, and it looks like that one's going to stick now. We're really excited about this also because this really starts to build us towards a lunar infrastructure future and towards the moonport vision, which Thomas presented on Monday of this week. So if you want to put something on the moon and you need a bit of support, we are that support. We've got power and we've got communications for payloads, and we are working on those considerations for going for very broad and wider range of potential systems to support. So if you're interested, talk to us. We'll be very interested. We've got a team ready and waiting, so to say, in Bremen. Looking forward to speaking to you about that. So thanks very much, everybody, and looking forward to some questions if everybody's still awake after all of that.
Thank you, Mark. I think we have a question already.
Hi, Mark. Thank you. Have you considered offering only the panels and the mechanism without the batteries? And how low could you get the mass in that case?
It had actually occurred to me to check before today to get the mass without the batteries. Yes, that's actually one of those really, I guess, one of those first steps as a potential alternative offering is looking at avoiding the lunar night survival problem, right, which is the big driver. So of course we're pushing towards this Oasis as a first development, as first unit, building some of that experience. But of course, from a modular perspective, it's very easy to leave the battery unit to one side. But I don't have the mass separately there, just the volume.
Thank you.
And we have a question from Ben.
Yes. I mean, Survive the Night box is very exciting. The example that you showed for your first one is the payloads aren't inside the box, they're on the surface. Is that what you envision going forward? And if so, are you providing thermal support for those payloads in both directions, not just providing them with heat, but also getting rid of the heat at local noon?
So that's correct. So from a nominal baseline on Oasis itself, there would be no shelter for the payloads. They are effectively on their own from a thermal perspective. The enabler for the lunar night survival is really the power. So we avoid, in fact, thermal transfer between Oasis and the payloads. Obviously, we can't avoid that completely. That would be fantastic if we could. But for now, we are also avoiding other elements which would interfere, such as using effectively Wi-Fi data or remote power. No, so they do just receive the power from us. They're then still responsible for their own thermal systems. One of the reasons to go like this means that we can stay payload agnostic, which is honestly a bit of a challenge here. Of course, we're more familiar with customizing solutions for individual payloads, but staying payload agnostic means that we can keep bringing these systems back again and again, and the payloads themselves have their own custom thermal solutions.
Thank you. We're just over time, but we do have one quick question in the middle here.
Very quick question. Do your payloads support movable payloads, essentially? And if so, how long are the tethers to allow them? How far can they move from the lander?
Sure. So the current baseline is 6-meter tethers. Oh, right. It's meant to be a quick answer, so I won't jump back. If you take a look at the picture, you'll see that does considerably constrain how far away from the lander the payloads can be placed. Yeah, that's definitely one of the key aspects for exploration science, is being able to place payloads on the surface itself. And so that's been a driver to go up to that 6-meter tether. Honestly, so having gone from 4 meters to 6 meters, an additional 2 meters is a considerable challenge on top. That's probably, I think, where it's going to stick at this point. Theoretically, at least, these sort of tethers can be produced in much longer lengths. They just get more expensive as you try to do it.
Okay, thank you.
Okay, I think we're out of time, but I'm sure you can find Mark later or maybe tomorrow. Right, the last session of this session and the last session of the day. Let's give a little bit of energy to our final speaker. We have Christian Janke, Associate Professor from Embry-Riddle Aeronautical University, and he's going to be talking to us about UAV-enabled subsurface geophysical mapping for extraterrestrial environments. Thank you very much, Christian.
All right, thank you very much for staying with me. I'm going to speak today about my favorite topic, which is drones, but this time drones in space. At Embry-Riddle Aeronautical University in TU Berlin, and with one partner in the US, we formed a multidisciplinary team out of drones and robotic experts, also geophysical mapping and space experts. I'm going to talk here from the perspective of Embry-Riddle, where we have the perfect combination of space and uncrewed systems. So we brought together and formed a team and said, after Ingenuity, what comes next and how can we put a payload on an aerial robot to actually do geophysical mapping, because we have an extensive background on that. And I'm going to start with some introduction, because UAV, uncrewed aerial vehicles, drones, may still be some in the development, some fast technology that not everybody can see the pace. So we have, they are used currently on Earth for several purposes, aerial sensing, detection methods. So remote sensing is obviously a no-brainer. Everybody knows they have electro-optical cameras, but they can be also used for subsurface measurement and prospecting of minerals, unexploded ordnance, mine detection, soil development. And we also have ground and maritime robots, obviously, that are used for those kind of purposes. So we talked to the colleagues who are also doing currently geophysical mapping on drones, and this is a bit of an overview. Some of those might be even new. If you see, it goes beyond geomagnetic mapping for metal in the ground, but it also goes into the area of ground-penetrating radar. And many, many other applications. Some of them are commercial off-the-shelf drones that you can buy, starting at 2,000 euro, but then it really goes up in self-made platforms, self-made sensors for all kinds of different traits that you can find on the surface, remote sensing for surface and even subsurface. So you can really go down into the earth and measure, and it's currently the standard way how prospecting, if you want to build a new site, if you want to detect mines. So the majority of that is currently being done actually with drones. So just one example that you saw on the previous slide, very interesting, one of my favorite sensors, the UAV gamma ray spectrometer that you can use for mineral exploration, but also for other use cases. not only for radioactive isotopes, but also for other elements in the ground that will give you a readout, and also for oil and gas exploration. So here, this is really one example that is now to be tested if it can be applied to space. In general, we, as we saw today, have some needs of extraterrestrial sensing and mapping. We saw that mapping Moon and Mars. So we need high-resolution data from aerial sensing, which is digital elevation models, topographical status, but also subsurface data is really important, and that can go down with the available sensors to density measurement, ice deposit detection, lava tube, and of course also minerals and commodities, as it is currently being done as well on Earth. And let's say in the concept, we obviously haven't tested it yet, but this is the concept overview. The UAV is equipped with lightweight geophysical sensors. The low altitude overflight, everything between 5 centimeter up to 5 meter would be the height that you fly over, and you could use that depending on what exactly you're looking for: ground penetrating radar, hyperspectral imagers, gravimetric sensors, magnetometers if they work into that environment. There are some obvious challenges that for us, if we build drones, are fairly new, because the flight controller of a drone is a very precious little device that is normally very prone to physical interferences. So, of course, everything as it has been built before on Earth, both the UAV and the flight controller, but also the sensors, must withstand solar radiation, the particles and everything. And it is also something that will have a lot of aspects of making the system very connected or making it very autonomous. We saw several examples actually today. Some of the systems we saw, rovers for example, and others have remote operation. Then they need a good data link, which can be a challenge. We are working on that as well. Or they are very autonomous, which makes them also very expensive. So there's a lot of computing power on there, and that does not cope well with the temperature variations and solar radiation, and maybe even for the flight controller, the low gravity environment. That was the biggest stepping stone for us to work on, because now we have seen that it's actually possible to apply our work from the past 15 years of drones, drone payloads, aerial robotics with geophysical sensors, also to the space domain. And here, this is the example of the ingenuity. We have here actually in the little silver box the opportunity to put a payload there and to use it. Many of you know that this was really going over the expectations. So it was designed for a very short amount of time and only some limited flights, but it exceeded that by far. So it's really a great opportunity to bring sensors to Mars and to mapping in the future. And some other enablers that we see currently in the technical development are the miniaturization that we have. We have extraterrestrial rotorcraft that many teams are currently working on, rotorcraft, but you could also technically use something that would be lighter than air, like balloons, and you would have independent autonomous systems that work there, energy efficient systems for flight. And if you decide to go down the road of autonomy, you can use onboard computing to do some pre-processing for your detection methods. So if you go to a field or you start testing somewhere, you could actually use sample data that you bring with you from Earth, from a test site, and then apply that to this environment. Here's a bit of an overview of how it would be possible. In general, you have your landers, you have the scout drones. They would work in conjunction, same as the Perseverance and Ingenuity did. So this is something you could really apply to many other scenarios with geophysical sensors, but also for quote-unquote normal mapping procedures, and just some examples how this could much better enable extraterrestrial crews to prepare for a certain area and work with that. Some further research that we are doing is actually not looking at the sensors, but also at the data links, because we anticipated that is really going to be needed in the future, that we have sufficient data link, both to the base station or maybe to Earth. And on the ground itself, if you are beyond line of sight, there can be some issues. So we are applying some measurements for data link, multipass bandwidth expectations that we have very successfully with an aerial relay. And this time the drone is used as a relay because you can use it for multiple purposes. In contrast to using it for the sensing, you could also use it for relay purposes. And some more development will be needed in some areas to have the comparable performance. So you need some ground truth. We heard that actually very often. We always try to have standard objects that we bury into the ground and look for it. So we forget where it is, and then we take the drone there and we actually see if we can detect it and measure it. And that is something we need much, much more also for the flight modeling. And in general, it's an excellent opportunity to combine that. Our team is still very early in the forming, but bringing these multidisciplinary aspects together, going beyond rovers and landers with UAVs, aerial robots using these sensors, it's a great opportunity to deploy the experiences that we can make from Earth also to extraterrestrial environment. And I'm very happy to talk about some other experiences and also some questions. And definitely, if you are working in this field for subsurface sensing, feel free to reach out to our team that we have here. We are trying to bring that together to a specific working group because it really, again, geophysical mapping, subsurface, aerial robotics, drones, and space are currently not so well connected, and we try to change that with our research group. So happy to take the first step and also standing by for your questions now. Thank you very much.
Thank you very much, Christian. Okay, questions? One over there.
Thank you for the great presentation. I was interested in altitude range up to 5 meters. If you could elaborate more on this kind of requirements, because I understand that, okay, you can improve the resolution, but also the coverage probably there will be less coverage for the drone. And if you do mapping, I guess this can also be a trade-off that you can consider. So I was genuinely interested in these requirements of the 5-meter maximum altitude for your drones.
Indeed, it is a trade-off. So for remote sensing, the higher you go, the bigger the field of view you have, but the smaller then, depending on your resolution, the ground sample distance is. But there are some geophysical sensors that require actually an almost extreme proximity to the ground, like centimeter level, which is also for us a big challenge. But you can work with onboard sensors that are laser rangefinders and visual odometry that would keep the drone in the right altitude. And it really depends on what you would like to measure. So GPR is definitely in the centimeter level. For geomagnetic measurements, you could also be a little bit higher, but not more than 2 or 3 meters.
Great question. There's one just in front.
Hi, thank you for the talk. Drone electronics are great, flight controllers especially, there's so many options nowadays, but have you experimented with adapting flight controllers that are built for propellers to spacecraft propulsion using thrusters?
Well, in the physical sense, they are currently not built for that, and the physical model behind it is not the same. The question that you are asking is, spacecraft in free Newtonian movement in contrast to something that is subject to gravity, to drag, to all kinds of other aspects that is actually also very hard to do. This is something, little tangent here, that FPV interceptor drones, kamikaze interceptor drones also experience these days, that it's harder to have a propeller-driven system from the guidance perspective than to have something that is rocket-propelled in terms of guiding it to a target, right? So we use commercial off-the-shelf flight controllers, and they are mostly designed for fixed-wing VTOLs or multicopters, yeah. And if you have an alternative, I'm happy to talk about it.
Any other questions? One here at the front.
Hi. For geophysical methods like ERT, what kind of depth would you estimate that these UAVs would be able to penetrate?
For what exactly?
For something like electrical tomography, if you can do that sort of wider range geophysical techniques.
Again, this is also a spectrum and a continuum depending on the transmission power that you have available on your drone. You could go definitely deeper. It's also a question of density and signal propagation in matter, which is different than in free space. So it's all a question of power available, I would say. If you have a stronger emitter, you can go deeper, but again, you have limited size, weight, and power constraints on a drone. So there's always a sweet spot in the middle. Compared to what we have been doing on Earth, it's down to even to 6 to 8 meters into the ground. That's possible.
Thank you.
Okay, next question. I'm not seeing any others, but thank you, Christian, for keeping us riveted
Thank you as well.
and interested right until the very end of the day.
Thank
well
you.
done. Okay, I think there should be a QR code that's about to come up on the screen. Yes. Okay, so all of our speakers have kept perfectly to time, so you've actually got 15 minutes back that you weren't expecting to have. So I want to draw your attention to the QR code. The QR code is our feedback survey for the event. It's open already. You do have one more day, but if you could all get your phones out right now, I want to see every phone. I want you to scan the QR code. I want it to be there in your browser so that you can fill it in when you get the opportunity. Thank you very much. Also, I would really recommend that all of you vote for the poster competition. All of the brilliant posters are out in the lobby. They've been here all week. We haven't had everyone vote yet, and we're really excited for that competition to draw to a close. It's going to be announced at the end of the day tomorrow, but we would like as many votes as possible to give us the best possible solution to who our winner should be. We want to canvass all of the possible votes, so please don't forget. Go and see the posters if you haven't already, and vote for your favorite if you have. Thank you very much. This is the end of the day. Thank you for staying with us, and I look forward to seeing you in the morning.